All right, so in this lesson, we want to look at the mean value theorem, but the mean value theorem for integration, okay? Now, if you recall, when we did the mean value theorem before, it was for derivatives. And what that said is that, if we have a function that's continuous from, here to here, okay, this is the average rate of change. And there will always equal some value of c where the instantaneous rate of change, in this case there's 2, equals the average or mean rate of change. Okay, that's what the mean value theorem for integration said. Okay? Alright, so that's the mean value theorem for derivatives. What we're going to actually look at here is we're going to develop this a little bit. We're going to use the fundamental theorem of calculus to show that the area of the integral from 1 to 4 of 3x squared minus 2x dx equals 48. Okay, so we've got this parabola. You can see it down here. We're doing the integral from 1 to 4. All right, so the antiderivative would be 3x cubed over 3, so just x cubed, minus 2x squared over 2, so minus just an x squared, plus the c. If I evaluate that, x cubed minus x squared from 1 to 4, that's going to give me 4 cubed, which is 64, minus 4 squared, 16. Minus 1 cubed minus 1, so then minus 0. So 64 minus 16 does equal 48. Okay, so we've just shown this. Now, what we have here is kind of a process here. It says find b minus a. Well, what's b minus a? 3, okay? b minus a is 3. And it says, find a value for f of c such that f of c times the b minus a equals the area. All right, well, f of c times the b minus a, well, we just said that that was 3, equals the area 48. Okay, well, that means f of c has to be 16. Okay? Now it says find c. Alright, well, if f of c is 16, that means that 3 times c squared minus 2c has to equal 16. Right? Okay? So, what we have here, we can solve this quadratic. 3c squared minus 2c minus 16 equals 0. Okay, this actually will factor if I do, let's say, a 3x, or not x, c, and a c. I'm going to do a plus 2, and I'm going to do a minus 8. So I'll have negative 8c plus 6c, and that'll give me a minus 2c in the middle. Okay? So that means that c has to equal negative 2 or 8/3, which is 2 2/3. Okay? Now, I got 2 different answers, but notice one of those 2 answers is in the interval from 1 to 4. Okay? And that brings us to what our mean value theorem for integrals is really telling us. If f is continuous on a closed interval from a to b, then there is a number c in the closed interval such that f of c is the average value of the function on the interval. Okay? And the integral from a to b of f of x dx will equal f of c times b minus a. Okay, so notice here we got c equal to 2 2/3. There's our c. Okay, f of 2 2/3 we know is 16. Okay, that right there is the average value of the function on the interval. Now notice, if I add 1 and 41 and divide by 2, I don't get 16. And that's the case because this is not linear. If it was linear, then yeah, I could just add 40 and 1 and I divide by 2 and the average value of the function would be 20.5. But here, it's curved. So they stay lower longer as we approach, and then it's increasing over here. We've got to find the average value a different way. Okay? So we have this relationship here. F of c times b minus a equals the value of the integral. Okay? So let's, here's kind of a corollary to that. If I were to solve this mean value theorem for f of c, it would be 1 over b minus a times the integral from a to b of f of x dx. That gives me the average value of the function. Okay? This one, well, this is the one that has the name, the mean value theorem. You'll probably end up using it in this form a little bit more. Okay? So that's the idea there. Okay? Notice it says there exists a number c. You can see right here in this example down below, it's possible, just like we had with the mean value theorem for derivatives, it's possible that you could have different c's that all have the same f of c. Alright, so you could have more than one, but this guarantees that we'll have at least one. Okay? So let's look at how this could actually be used. All right, this is kind of a wild looking one, and I highlighted some things because the initial formatting was a little hard to see. The speed of sound. Speed of sound is kind of interesting. If you've ever been to a baseball game and you sit far away and you see the batter swing the bat and hit the ball, and then like a second later you hear the crack. Or if you see a lightning storm and you see lightning off in the distance, and then a few seconds later, you know, you hear the thunder, which by the way is a good way to tell about how far it is. It's about a second a mile, estimated. But here, at different altitudes on the Earth here, the sound actually travels at different speeds. Okay, so notice here, this is all in meters, x is kilometers. So between 0 and an 11.5 kilometers, the speed of sound actually gets a little bit slower the higher you go. Okay? Then between 11.5 kilometers and 22 kilometers off the surface of the Earth, the speed of sound is a constant 295. And this is meters per second. And then between 22 and 32 kilometers off the ground, it is growing linearly again. Between 32 and 50, it's growing linearly at a little different rate. And then here between 50 and 80, it actually starts slowing down again. Okay? So it's interesting here. So what is the average speed of sound? Okay? what's the average speed of sound from 0 to 80 kilometers, which I think that's the entire Earth's atmosphere. Well, how do you propose we do that?
Mean value for integral.
The mean value theorem, okay? The average speed of sound is going to be that mean value. So,
You have to find the average to all of those and add together.
well, let's take a look at and set it up first. So this is going to be the average speed of sound. Let's just call that S of C. Okay? And that's going to equal 1 over b minus a times the integral from 0 to 80 of s of x dx.
So what, they can split it up into like 5 different integrals?
Yep. Okay? So, in this case here, because it's a piecewise function, we're going to be doing a number of different integrals. Okay? But notice here we're using this same formula. The mean value is 1 over b minus a times that. Okay? So let's go ahead and start working this out. S of c is going to be 1 over 80 times, and now we have our different integrals. Okay? So it's going to be the integral from 0 to 11.5 of a negative 4x plus 341 dx. Plus, I'm going to work down here a little bit, plus the integral from 11.5 to 22 of 295 dx. Plus the integral from 22 to 32 of 3/4 x plus 278.5 dx. Plus the integral from 32 to 50 of 3/2 x plus 254.5 dx. Plus the integral from 50 to 80 of negative 3/2 x plus 404.5 dx. Okay? So we're multiplying 1 over 80 by all of that. Okay? Let's divide and conquer a little bit. That would be nice. Let's see. Can you guys, Adam and Jessica and Flora, can you guys do the first integral? The 0 to 11.5? Can you guys do, I'll do the second one. Can you guys do 22 to 32? All right. Can you guys do 32 to 50? Actually, all 6 of you can. And you 4, can you guys do 50 to 80? Okay.
50 to 32.
No, we're doing 50 to 80.
They're doing 32 to 50 there. You're doing 50 to 80. Okay? Okay, so I think we've got them all here. These are what you're doing. Okay, so we have 1/80th times, what'd you guys get for the first one? 3657. 36.57 or 3,657. Okay. And then plus 3,097.5. Okay. Plus, what'd you guys get for the next part?
2,987.5.
Okay. The next part?
5,688.
All right, in course. And the last part?
9,210.
9,210, okay. So, when we add all those up, okay, we have 3657 plus the 3097.5 plus the 2987.5 plus the 5688 plus the 9210. We get 24,640. And we got to do 1/80th times that. So 24,640. Okay. Divided by the 80.
313, I think.
308.
8, sorry.
There you go. It's okay. So 308 meters per second, because this said that that S was measured in meters per second. So 308 meters per second is the average speed of sound based on this model. Okay? If we were to figure out exactly where that occurred, like where along that whole thing does this occur, that would tell us the altitude at which we had the average speed of sound. Okay? Now that could get a little complicated because we'd have to basically set each of the pieces equal to 308 and then make sure that the answer was in the interval. Okay?
Wouldn't, so we got the f of c value, so that's like technically the y. So
Yes.
why is that not like the altitude?
Well, based on how we defined our variables, x is the altitude in kilometers. This function is written so that when you plug in the altitude, it gives you the speed of the sound. Okay? So that's how we can find, in this case, the average value of a very complex function with multiple parts. You simply take the integral, multiply by 1 over b minus a, and there's your average value. Okay? So, if we have a velocity function and we want to find the average velocity, now we can take the integral from start to finish and divide by 1 over b minus a. Which, what are you getting when you do the integral of velocity?
Position.
Position. Position minus position over the difference in time. It actually, you end up doing the same formula that we've done in the past to find average velocity. Okay? We're just coming about it from a different angle. Okay? So, that is our mean value theorem, average value of a function, and that's it.